Okay, so to continue our program, we're in just a moment going to look at quantum computing, the next disruption. We do have another polling question for you, if you have your devices handy. And that question is, when will quantum computing technology become materially important in the industry? Over the course of either within the next 3 years, the next 5, the next 7, the next 10, or sometime after the next 10. If you could submit your votes, and when we talk about the next disruption and what's perhaps over the horizon, this will give us an audience view as to just how far distant that horizon might be. If we can have a look at the results, we've got a pretty even spread. That's interesting. We'll give that a moment while it's still adjusting and settling. So we'll have Michael and Conan on stage in a moment, and they can tell us just quite what is the right horizon that we should be thinking about. So let's continue our program. As we look at the quantum computing with Michael Brett, Chief Executive Officer of QX Branch, and as you'll hear in a moment, and I'm sure my countryman Chris down here in the front row will agree with me, Michael has the best accent of all of our speakers today. He'll be joined by my colleague Conan French for the conversation. Conan has plenty of his questions once again, but he will also invite and work in any questions that you submit via the app. So if you have your burning thoughts, please send those through, and Conan will add those to the discussion. But please join me in welcoming Michael and Conan to the stage.
Thanks very much, Brad.
G'day. Hello, thank you.
Your sense of theme and accents. So one of our roles here in the IF Digital Finance Unit is to look over the horizon and see what's coming next. And I think that we've had a pretty decent track record of this over the last 5 or 6 years. And one of the topics that Brad and I have been putting on the agenda for the last year is quantum computing. And this is one of those words that, that word alone has definitely risen in the public consciousness. You've seen it in a lot of media coverage. People are starting to talk about it. You're starting to hear, oh, it's the next big thing in the industry. But not many people are able to really dig below that and see, what is this? What is it that we're talking about? And so that's why we're excited to have Michael join us today, somebody who has been a technologist building technology solutions across different sectors of the industry and the economy, but is also working on the application layer. So somebody who is staying close to that hardware science of quantum computing that we'll dive into for a minute, but also starting to think about what are those things that we can build, and that's because Q Branch really came to it from a predictive analytics view. And so maybe if we could start off how your voyage to quantum, and then we'll dive in to sort of everything that everybody needs to know in 5 minutes about quantum computing before we can step off from there.
Yeah, sure thing. So the origin story to my company, Q Branch, starts in the aerospace and defense world. My personal background is in aerospace engineering and building modeling and simulation software systems that could do things like risk analytics and mission planning and a lot of numerical analysis that has a lot of features that are similar to what we all deal with in the financial sector as well, like large complex models with a lot of computational power requirements. And Lockheed Martin, who we were working with at the time, had just bought the first quantum computer ever back in 2011 and introduced our team to this new technology and said, hey, would you like to see if you could apply some of your numerical work on this new type of computer? And we jumped at that opportunity to do it. So it kind of came in sideways to both quantum computing and the world of financial tech, but it's been a good journey since then.
So maybe now let's look at that. What is a quantum computer? What is quantum computing? How is it different from classical computing? What are some of the essentials, and why is it such a big development and a big break from what we've seen before?
Yeah, so one of the exciting things over the last century really has been the development of computational technology, and we've been riding this wave of Moore's law, where the computational power of computers has doubled every 18 months or so. And one of the key features that's allowed us to do that is by shrinking the size of transistors down to very, very small transistors. So each individual transistor that sits in your pocket, in your iPhone, or on your desktop computer is becoming smaller and smaller every 18 months or so. But we've reached the fundamental limit of how small we can make a transistor. It's sort of got to the point where they're counting the number of atoms to make sure there's enough electrons to make electricity flow. And so people that build computers are using different techniques now to get more and more performance out of those systems. Now, quantum computing asks the question, well, what if we go even further down? What if we go sort of into the basement of this technology and look in the quantum physics realm of computational science? So what if we go inside the atom and use the weird, strange behavior of quantum physics, which could allow us to do a different kind of math, which could allow us to do a different kind of algorithm, which means we could build a different kind of application to do that work. And so that's what quantum computing is. It's using the strange behavior of quantum physics to then access a different kind of mathematics that we can't do efficiently on a classical computer.
And the can't do and efficiently, I think, are the essential elements. So what is it that a quantum computer, in these early days seems well positioned to do differently, and give us a sense of the order of magnitude on efficiency? Why are people so excited about this?
Yeah, it's incredibly exciting because using that different kind of physics and different kind of math, quantum computers are able to solve some problems that are very difficult for classical computers to solve. So there's some problems that even today, with all the compute resource that we've got in the cloud, are still extremely expensive or extremely time consuming to solve those problems. And quantum computers can help us unlock those and shrink the time to solution down to something that's much more manageable for us in business or just day-to-day life. And so to give you a sense of what those kind of problems are, it's like in portfolio optimization or risk management, every new variable or every new stock that you add to the basket doubles the size of the compute time, becomes exponentially more difficult to solve. Quantum computers have got some features that could allow us to do that in linear time. So instead of doubling the compute time, it just adds a little bit more to the compute time there. And so that could change the way that we approach some problems in the financial sector. Rather than having to use heuristics to sort of work around that or compute once a day, we might be able to take that compute down to a few minutes and then change business processes around that.
So as you look at those capabilities and you think about the financial service companies that you're working with, what are some examples of how you're going to apply that? So it's still early days, you're still, I think, in testing and experimentation, but it seems that there are definitely some applications that are emerging early. So maybe a little flavor of some of those and some examples that you can share.
So the way to think about where we are with quantum computers today is we're sort of at that stage of a technology where it's exited the research labs and the universities and now into commercial R&D. So we've got prototype systems to work with, developmental platforms to work with. So companies like IBM, Microsoft, Google, and there's some startup companies out there as well, have created these essentially developmental systems that we can start to explore and to validate applications with. And it's kind of like having access to a really early prototype iPhone before it gets released, that we're now looking at, well, what will the first apps in the App Store be? On the day that this is commercially ready, what are people going to access and start to use on that first day? So the kind of customers that we work with at QBranch are large financial institutions that are interested in understanding what that application could look like for them. So on day one, when they turn it on, looking at things like portfolio optimization, risk management, improving the training time on machine learning algorithms so that they can do better compliance type activities. All of those functions that are really expensive computationally, is there a breakthrough that we could have with a quantum computer, and then the first mover advantage that comes with that.
Yeah, and that first mover advantage, I mean, I think you see a lot of coverage about that at a national level. So there's been development in the US, Canada, you see Europe making a big investment to try and drive quantum computing there. You see China, again, realizing the power of this. And I think some of that challenge has been driven by the implications for encryption. So we could spend a whole day-long seminar probably on that topic alone. But maybe again for the crowd, what is it that quantum introduces into the encryption environment, and how do you think folks will deal with it?
Yeah, so one of the applications of quantum computing is the potential to de-encrypt some of the commonly used encryption algorithms very, very quickly. And that's because there's an assumption that sits behind a lot of the encryption algorithms that we use, that it's assumed it will take a very long time to work through a particular mathematical problem. But quantum computers, using the strange physics and then the strange mathematics, are able to do that very, very quickly. And so there's an effort going on right now to look at post-quantum cryptography. So what are the standards that we'll have to adopt in the encryption world that would be resilient to quantum computers once they become available? And so if you're a regulator or a large institution that's concerned about this, the National Institute for Standards and Technology here in the US is working through that process right now, defining what these next generation algorithms need to look like and their recommendation around that. And I know that some regulators, and I think the MAS in particular in Singapore, are looking at, well, what's the industry-wide implication of this? And it's kind of like running through a Y2K type problem again, where we've got a large threat that's looming. We've got a little bit of time to deal with it, but it's of very high importance to take some action on that. And so follow the advice of the regulators that are coming out.
So quantum resistant encryption is sort of one important development area. What are some of the others I think you're doing some work with UBS, and maybe any more detail on what they're seeing in sort of new modeling techniques?
Yeah, it's very much an exploration phase right now for a lot of institutions, trying to understand for themselves what quantum computers are and build up organizational capability. So what kind of workforce do they need? What kind of processes do they need to understand it? And then also just what kind of applications could it mean to them? So we've been working very closely with UBS. We just finished a large project with them looking at a foreign exchange market making optimization problem and seeing if we could expand the number of currencies that they could include in their optimization work and then benchmark that against how they do that today on their classical systems. And there were some really promising results out of that. It's not a huge breakthrough. We're not going to see this go into production anytime soon. But the mere fact that we even got to a benchmarkable system, one that we could characterize and compare between the classical and the quantum and see how that worked, we can now start to see where that crossover would be on performance and when it becomes an economically viable application for them.
And in addition to thinking about classical computing power there, and what changes when you move to a quantum environment, there's also still in this early phase some different approaches to the principles of quantum physics that are being employed in different hardware machines. And we don't have, again, a lot of time, but maybe a little flavor of some of the developments that you see coming out of some of the different hardware shops.
It's a really exciting moment for the quantum computing hardware folks, and there's a number of different ways to build a quantum computer, and we're just not sure yet which one is going to be the most viable approach, or there may in fact be many ways to build a quantum computer that have different attributes that are useful for different applications.
And I think that's the main question.
Yeah.
Do you see that sort of emerging where you have different hardware types might be better suited for different applications?
Yeah, I think so. They've got very different attributes and being an aerospace guy, one of the ways that I think about this is that helicopters and aeroplanes are both flying machines, but they've got very different applications to them. So one's good for really long distance type work, others good for short distance transportation. And so it's a similar kind of concept in quantum computing where one architecture will be very well suited to some applications and other architecture to others.
And as we think about the policy environment, you mentioned one aspect, which is thinking about the security implications and cyber implications of post-quantum encryption. Are there some other things that you think early on, does data policy shape how quantum grows and develops, and do you see some of the data policy developments in different regions shaping quantum in a different way? So for instance, would Chinese quantum maybe grow up in a different way or a different environment from European quantum machines?
Potentially. Quantum computing is a sort of inherently cloud-first technology. So we'll see quantum computers be adopted into the various cloud offerings around the world. And we already use a mixed compute environment in the cloud today. So we've got CPUs and GPUs and then other processors all running alongside each other. And quantum computing will just be another tool in that toolbox that'll solve some problems. And so a lot of the same policy factors that impact the cloud will also impact how we deal with quantum. Some that I'd highlight are particularly things around explainability, which was on the last panel. That's going to be a tough one. Like it's hard enough already, but now we've got to explain quantum as well. Things like repeatability and assurance around algorithms. If you're using the weird behavior of quantum physics, which is a kind of inherently random type environment, how do you show a regulator that, yeah, we can rely on this and it's a repeatable type experiment as well? And so working through that's going to be tough.
And Tim Adams, some of you may have heard Tim Adams open the day with one of the quantum physics puzzle observations that the cat is in the box and the cat is also in the box and it's dead and it's alive. And that's, again, a little snapshot of the way this physics is a little different than the binary Boolean logic that we're sort of moving out of in the past era. And so again, as we...
It's a tough one because everyone focuses on the cat too much, and we feel very bad for the cat. But another way to think about it is if you've got a spinning coin in a box. So you flip a coin in a box and is it heads or tails? While it's spinning, it's both. It's some probability that it will become either heads or tails. When you open the box, it resolves as one way or the other. And the trick in quantum computing is that we're able to manipulate that probability while it's spinning in there. And so you can take that one home with you as a non-cat metaphor for how this all works.
And much better for financial markets as well. Any last parting thoughts, as people think about where are we? I think you gave us some good examples of where we are in the development curve and what's coming. But as we think about the distribution there, I think people are really wondering, okay, is this something I'm committing mindshare to today? What are the types of organizations that really should be committing some effort? Where are they? What are some proofs or applications that you would love to be building? Any message to the financial services industry?
This is a technology that's emerging very, very quickly, and the time to start is now in understanding this. So it wouldn't be the correct strategy to wait until quantum computers are in the market and then start, because you'll be beaten in the competitive landscape on that. And with the developer platforms that we've got available to us now, we can do a lot of really good work in not just science, but genuine development in capturing IP around the applications that'll be those first apps in the App Store once this technology comes to fruition.
And the last question, are there any apps that aren't in development today that you think, gee, it'd be really great if the following type of institution wanted to test something out, or any areas that you think are under represented in applications?
I think that the potential for reducing the training time on machine learning is going to be one of the big breakthroughs in quantum computing. If we can take that cost of machine learning right down, get more loops and human design involved in the machine learning applications, that's an enabler to artificial intelligence type things. And so, I'm thinking far ahead here, but I think that's exactly where we're headed with this technology.
Excellent. Well, thank you so much for coming and sharing your view on the developments today.
Great to be here.
Appreciate it.